In this video, we will review vectors in Rn. It is likely you have seen these vectors before because in math and physics, the term vector is applied to a wide variety of applications and objects. So we are going to start by describing vectors in Rn, the concept of the geometric vector, and then later in subsequent videos we will progress to more abstract and general vectors. So again, this does assume you're comfortable with vectors. If not, you might want a more comprehensive treatment of this material, but I will go through the important concepts here. In particular, I will talk about vectors in Rn, both how to get them algebraically as well as looking at them graphically. We'll do some examples, these examples here, and also give geometric interpretations to these vectors. We will start with vectors in R2. They should be familiar, if not just flat out friendly for you. So we'll look at the vector 1, 2. Often we interpret that as a coordinate in the Cartesian plane. So that would be the coordinate 1, 2, where we go over on the x-axis 1 unit, and y we go over 2 in the y-axis 2 units. So this is our point 1, 2, and then we draw the vector from the origin to the point 1, 2. And something worth noting, technically then, I can move this vector anywhere because actually technically a vector is just magnitude and direction. So as long as I am careful and move it with the same angle and preserve the angle, basically preserve the direction, this vector is the same. But in this class, we will root all of our vectors at 0, 0. Our next vector, for example, could be the vector 3, 2, where we go over 3 on the x-axis, up on the y, 2 units up on the y-axis, and then our vector negative 1, 2. So we go over negative 1 on the x-axis and up 2 on the y-axis. And again, technically, we can move these vectors around. Let me get this one. And this is still the vector, this here is still the vector 1, 2. And this vector here is still the vector 3, 2. But again, in our class, we will root all our vectors. We'll have their starting point at 0, 0. Vectors in R3 are a little more challenging to draw, but they're doable once you get used to them. So here's my x-axis, here's my y-axis, and here's my z-axis. And I want to plot the point 1, 3, 2, or the vector 1, 3, 2. So I go over 1 unit in the x-axis, along the x-axis, and our units are parallel. When we draw our lines, they're going to be parallel to the y-axis. We go over 3 units, 1, 2, 3, in the y-axis, and then we draw the rectangle between the x equals 1 and y equals 3. So that's the start. And now next, we're going to kind of draw at z equals 2, we're going to look at this line here and kind of draw up the plane parallel to it. And then this will give us the point for our vector 1, 3, 2. So the idea is that from here, when you're in the z equals 0 plane, you map out your x and y, and then you go up 2 units, if you notice 1, 2, from here to the point 1, 3, 2, because there's some dimension here, so we don't draw up to here. We start from the plane, the 0 plane, and then go up. And I'm not even going to move this vector around because it gets really confusing there. Next, I'm going to draw the vector negative 1, 2, 3. And I am going to start by marking where x is equal to negative 1 and y is equal to 1, 2. And I draw over here from the point y equals 2, a line parallel to the x-axis, and on from where x is equal to negative 1, remember I'm going backwards on the x-axis. This is, in the positive direction, 0. This is back 1 unit. I draw a line parallel to the y-axis, and I get this point here. So this is in the z equals 0 plane. It is the point negative 1, 2, where x is equal to negative 1, y is equal to 2, and theoretically I should go 1, 2, 3, so I should be somewhere around here for my point. And I can also sort of draw that, so now my box is going to look at 3. I'm trying to draw this line here parallel to this line, so I'm drawing up to my point negative 1, 2, and then I draw my box, and now I can have my vector. Oops, that wasn't a very good one. My vector here. And it is approximately from this point, if I say this is the z equals 0 plane, it is approximately 3 units up from here. Again, we don't start down here and count 3. We need to, take into account the dimensionality. So we start here at the z equals 0 and go up 3 units. Next, we'll look at vector addition. So vector addition is a lot like, you're used to it from adding points. So if you have the point 1, 3 and 2, 1, we can consider that the vector 1, 3 and the vector 2, 1. And we add component by component. So we add the first component and we get 3, the second coordinate and we get 4. What that is geometrically, so I've plotted my 1, 3 vector and my 2, 1 vector. Geometrically, I'm going to take this vector and I'm going to move its tail to the head of the other vector, and this will be, so basically I have this vector and then I add on my second vector, and that, the end point, will be the vector of my 3, 4. So you can see that this geometric interpretation of just taking one vector and putting the end of one vector at the beginning of the other vector, or vice versa, the beginning of this vector at the end of this vector, will give me the vector addition. Also, some people like to think of this as this parallelogram kind of look. So I just move this over. So its beginning is at the end of this other vector, and then I have this parallelogram, and I just go from the diagonal, and that will give me my new vector. So geometrically, vector addition is taking the beginning of one vector and moving it to the endpoint of the next vector. Remember before I had told you that we always put our vectors at the 0, 0, but really we can move them around, and as long as we preserve the direction or the angle of the vector and the length of the vector, we're okay to move it through space. So that's exactly what we did here. We took this 2, 1 vector and we placed it right here. So its beginning is at the end of the first vector. It's sort of like if you're walking, you can say, oh, this is my first path, and then my second path, if I know I go in this direction for this long, well, the end of my entire path is going to be here. For the scalar multiplication, we know how to do that, and you're probably used to this. So if you multiply 2 times 3, 2, and I just wrote it in vector form, 2 times the vector 3, 2, I get 6, 4. And geometrically, what that does is you have a vector in the same direction, but now it's going to be twice as long. So I'm still going to go over another 3, and then from here I'm going to go up 2. So it's roughly here, my 6, 4. And then if I had multiplied instead by 1/2, 3, 2, I would have gotten the vector 1/2, 3, 2. I would have gotten the vector 1 and 1/2 and 1. No, I should have gotten 2. No, 1, right? Because it's half of this. I'm sorry, I was looking at the wrong thing. That would be the vector somewhere here around 1 and 1/2 and 1. So it would just be this much, or half the length of the vector 3, 2. That's also why they call it scalar multiplication, is because you're just basically scaling the vector. You can make it longer, you can make it shorter. So when you multiply by a scalar, you're scaling your vector. And now we have some more examples. We want to give a geometric interpretation of the subset W of R2. So R2 is the XY space, the XY plane, and we have a subset of that plane, and we define that as vectors x such that x is equal to x1, x2, where x1 plus x2 is equal to 2. Thinking of this vector coordinate as sort of a xy pair, so what you have here, that what this equation is expressing is that x plus y is equal to 2, right? So if your x2, if you think of that as a y coordinate, and your x1 as an x coordinate, you have x plus y is equal to 2, which is just the line y is equal to minus x plus 2. So here is my drawing. So w is the line y equals minus x plus 2. Another example, give a geometric interpretation of the subset W of R2 defined by x, where x is equal to, this looks like R3. It's x1, x2, and z is equal to 1, and x1 and x2 are real numbers. So I changed this to R3. But anyway, this tells us that x1 and x2, they can be any real numbers, but we have in the R3 space, in three-dimensional space, we have z set equal to 1. So essentially what we have is the plane where z is equal to 1. Again, because you can choose any point on this plane, and z will equal to 1, and x and y will be some other values. They're different values along the plane. So we've covered our main topics and examples in this video. I do have a couple of more examples to show you, but this is a very cursory review. So if you need to look at other resources for more examples, I would encourage you to do so. This is not cursory because it's not important. It's cursory because I figure you probably have already done this before. So just a quick example, if u is equal to 3, 1, and v is equal to 1, 2, we want to sketch u, 2v, u plus 2v, and v minus u. So here I have u is equal to 3, 1, so I went over 3 units on the x-axis, up 1 on the y. Here I have v is equal to 1, 2. I go over 1 unit on the x-axis, up 2 units on the y. Next I want to look at 2v. So 2v is just the vector v in the same direction but twice as long. I can also do this algebraically by multiplying 2 times v, which gives me 2, 4. So here I have 2, 4. And last, geometrically, I can think of completing this parallelogram. So here I have the side that's perpendicular to 2v. Here I have the side that's perpendicular to u. And then I complete my parallelogram, and then from the origin to the other endpoint of the diagonal is my u plus 2v. I can also do this u plus 2v algebraically. I can take my u plus 2v, and I will have 3 plus 2, which is 5, and then I have 1 plus 2 times 2, which is 4, so 1 plus 4 is 5. So I can verify that 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5. So this is approximately 5, 5. You know, my parallelogram could have been drawn a little bit better, but here it is, 5, 5. Now to start my v minus u, that's the same thing as v plus negative u. And negative u is the same vector as u, except in the opposite direction. This should be the same line if I had been better about my drawing. But anyway, so you can also do this algebraically, multiplying u by a negative, you get minus 3 minus u, so minus 1. So here's my negative u. So now to do v minus u, I'm going to add v plus u. I'm going to take my v vector and put it at the end of my u. I'm then going to take my u vector, so I complete this parallelogram. And then finally I can draw my vector from the origin to the other point on the diagonal of my parallelogram, and I have v minus u. And also I could do this algebraically. V minus u, I could take my v, my 1, 2, minus u, which is minus 3, 1. I can calculate it as minus 2, 1, which certainly looks sort of like what I drew here. For our next example, we have x is equal to 0, 1, 3, and y is equal to 2, 1, 0, and we want to sketch x, y, and x plus y. So this is trickier because it's in 3 dimensions. So I will start with x, which is 0, 1, 3. So I go no units along the x-axis, 1 unit over on y, and then I go up 3. So x isn't bad. Now I need to do y, 2, 1, 0. So I go over 2 units on the x. Actually, this was probably too big for 1 unit, but let's just pretend this is 2 units. And then 1 unit on y. And I draw from y equals 1 a line parallel to the x-axis. And then along the line at x equals 2, a line parallel to the y-axis. And where they intersect, that's my point in the z equals 0 plane, where x equals 2 and y equals 1. And now I need to go up 0 units. Oh, that's nice. So this is my point y. Next, I was going to somehow try to do a parallelogram, but then I thought, you know what, I'm just going to do this algebraically. So I added x plus y, and I get 2, 2, 3, and I graphed it, coming out 2 units on the x, 2 units on the y, and then I kind of drew my parallelogram, And then I go up roughly 3 units from here because now I'm at z equals 0, so 1, 2, maybe up to here. And then I get, or you can draw your parallelogram here. You know, you draw your line from 0 up to the tip of this point of x equals 2, y equals 2. And then you draw your line perpendicular from up here, perpendicular to the z-axis, and then you get your vector 2, 2, 3. So now that we've gone through some additional examples, I'll have review problems for you to try. Here are 3 review problems with parts A, B, and C for you to try. So pause the video, give them a try, and then I'll have solutions on the next slides. These are the solutions for the first problem. Solutions for the second problem. And solutions for the last problem. And that is it for this video. Thank you for watching.